Hi, this is Emma Vierheller, and this is my 5170 final presentation. The question that's been driving my inquiry and will drive this presentation is students have been working on constructions and they've constructed an equilateral triangle, a hexagon within a circle, a square, a rhombus, a perpendicular bisector, maybe a pentagon. And now they're saying, okay, well, if I can do all of these things, can I create any regular polygon? And that's a really natural question that comes up, and I'm really excited to talk a little bit more about it and dive into that question. So, a couple of standards that we're looking at specifically, both obviously within the geometry domain, specifically congruence, is that students should be making formal geometric constructions. They can use a compass and a straight edge, they can use string, they can use reflective devices. I like to use patty paper, we fold paper, and then you'll see an example of some dynamic geometry software later. So they should be doing a lot of things: copying line segments, constructing perpendicular lines, bisectors, squares. They should get really comfortable with those constructions, and specifically too, what makes those constructions work. Secondly, here are the explicit constructions that students need to have created: an equilateral triangle, a square, and a hexagon inscribed in a circle. So those are constructions that obviously students are very much expected to be able to complete, and then this is implicit and be able to understand why those things are working. So, before I dive into the math, this is an assessment question that I ask students. I ask students to construct an equilateral triangle and explain how you know that this triangle is equilateral. I've noticed that students are very good at repeating the methods. An equilateral triangle is not a difficult construction by any means, but sometimes it's hard for them to express exactly why they know that their triangle is equilateral. So, the tools that students are using are a straight edge and a compass. Even if you're using dynamic geometry software, the methods here, the tools we're using are essentially the same. We've just digitized them. We're going to use a straight edge to create straight lines. We're not going to use them to do the measuring of a ruler. And then we're going to use a compass that's used to draw the circle or an arc. And a compass is really what's important here when we're distinguishing length. Length is not measured using a ruler. Length is measured using the setting of a compass to create a circle with a given radius. And we're going to talk a lot more about that in just a moment. So, to get your feel for a couple of constructions, what I have here is constructing an equilateral triangle. This is something that students get pretty familiar with pretty quickly. And the essence of what's going on here is we've copied that black line segment, the length of it, onto the red line segment. The compass was set at that certain mark, and the arc that was created marks off the same length that was originally there from the black. From there, we're going to keep the compass setting the exact same, and that's what's preserving length in this case. So with the compass setting the exact same, we're going to swivel that compass and we're going to make two arcs on top, one with the compass point being on the left and one with the compass point being on the right. So there's that first arc coming from the left, and then keeping the compass the exact same setting, we're going to move it over and we're going to create an arc on the other side. Now that intersection is the one place above the red line segment that is the same distance away from each of the endpoints. And that's crucial for creating an equilateral triangle. So we'll see those things being connected. And there we have an equilateral triangle construction. And like I said before, this is something that I ask my students. I ask them to do this construction. And then I also ask them how they know that this is an equilateral triangle. So, getting to the heart of it all with Euclid's elements, there are three axioms that are really guiding our work right now. The first is that we can draw a straight line from any point to any point. And that's something that students kind of intuitively think about. Yeah, I can connect any 2 points I want with a line. Second is a straight line can be extended indefinitely. And then finally, and maybe arguably most importantly for this talk, is to draw a circle with any center and any radius. So if I can draw a circle with any center and any radius, then that means that I can preserve any length that I want, and that's going to be really critical. We also need to define what it means to be constructible. And polygon is constructible if it can be created using a finite number of intersecting circles and lines to connect points. There's no cheating here. We're not using anything other than the methods of bisecting angles, constructing perpendicular bisectors, and making sure we're really abiding by those three axioms on the previous slide. Some things that Euclidean constructions include, perpendicular bisectors and bisecting angles are going to be really crucial to the work that we're doing right now. The parallel line, we have the infamous squaring of a circle. So that was a really interesting problem that was proposed by Euclid, is how do we construct a square in a circle that occupy the same area? That's a really interesting thing to think about. And then obviously an equilateral triangle and a hexagon. Okay, really quickly, I want to show you just a quick square inscribed in a circle, because this is going to be really similar to some of the work that we're doing. So if we're constructing a square within a circle, what we need to do is we need to create a diameter. And from that diameter, we are going to construct AC's perpendicular bisector. And that's obviously going to go through the center of the circle if AC is a diameter. So we're constructing that perpendicular bisector. And once we've done that, we've located the 4 vertices of the square. So the 4 vertices of the square are going to live at A, at this point, at C, and at the point below, and we can name those as well. And there's our construction of our square. Notice how important the perpendicular bisector was defining those 2 other points. Okay? So to really give you an in-depth idea of what's going on when we're doing these circle and straight edge constructions, we're going to go through the construction of an octagon. I'm using dynamic geometry software. I'm using GeoGebra versus using a compass and a straight edge. The mechanics are absolutely the same, except for I'm not always great with the compass. My hand shakes a little bit, and so that can make things a little bit more difficult for me. So we're going to embrace the 21st century here. So we're going to start, and here's our line segment AB. And the first thing we're going to do is we're going to construct 2 circles that both have a radius of AB. And we're going to construct the perpendicular bisector of A to B. So using points C and D, through any 2 points, we can create a straight line. And so we're going to create that straight line, and that's going to become the perpendicular bisector. I often tell my students that the perpendicular bisector is one of the most important, if not the most important construction we do. It's really intuitive with paper folding. So what we're essentially doing is that perpendicular bisector reflects A onto B and B onto A. It cuts AB in half, as well as creates those 4 right angles. And so that becomes supremely important when we're talking about transformations in regards to reflections, as well as being able to construct right angles. And then we can start playing with this a little bit more. So now we've got this circle here, okay, and this circle has a radius of AE. It has a circle that's half the radius of the 2 original circles. And we'll create some more points. And right now what we have is, I'm going to get my pencil tool for a second. What we have is we have 4 corners. And if those 4 corners were to be connected, we would have constructed a square. Now what we need to do is we need to bisect these right angles. So angle FEB, angle BEG, angle GEA, and angle AEF. We need to bisect those angles. Because right now we've got our 90-degree angles, and if we want an octagon, we need 4 more points, 4 more vertices, and they're going to come at the halfway point of each. So next, we need to start figuring out where those points are going to be, okay? So the importance of these 2 green circles is these 2 green circles are helping us bisect the angle from F to E to B. So here's angle FEB, okay? What we did is we constructed 2 circles here, and their intersection right here, when we connect E to that intersection, it's going to be a much straighter line, okay? That's going to have bisected that angle, and the intersection will give us another vertex of our octagon. So that point H is going to be connected, and now we have angle F to E to H, which is a 45-degree angle because we're bisecting a 90-degree angle, and then H to E to B doing the same thing. Okay? Now, a lot more stuff goes on. I'm going to walk us backwards a little bit. I kind of wanted to show you where we were getting at the end. Okay? So now, we've got these next coordinates going on here, and we've bisected the angle on the other side. And now we have these new points. We have the points L, E, J, B, M, G, K, and A. And each of our 90-degree angles were bisected. So those are all 45-degree angles, and those new black points are all halfway between, on the circle at least, between A and E, or A and F, and so on and so forth. So then what happens is that our octagon is constructed out of those points. Now you'll notice the methods that we're talking about here. We had that square originally constructed, and then we bisected each of those angles. We can bisect any angle that we want. So that idea of bisecting an angle and therefore creating double the number of vertices in a shape is really important to understanding what type of constructions we're actually allowed to perform. So what's happening here is the land of mathematics and constructions are largely, there's some cool investigations going on, but Euclid really lived in those basics. And those are the same basics that our students are pretty comfortable with. But we want to answer this bigger question. What about something that's not 4-sided or 6-sided? What about something bigger? Is that possible? And so that's what we're going to start diving into, is what's possible in this case. Now here's where things start to get interesting. So, in 1796, Carl Gauss constructed a 17-sided figure at the ripe young age of 19, which doesn't make any of us feel bad for what we have not accomplished and yet being considerably older. So this is a huge leap forward. And what that makes me start to wonder, and would probably make my students start to wonder, is what's so special about 17 sides? So far, the only odd-sided figures they've really seen is an equilateral triangle and perhaps a pentagon. And they might understand that you can start doubling sides, but then things end up turning even and things like that. So this is a really interesting number to think about, and why a 17-sided figure is constructible. So we're going to move ahead then to really getting at the heart of the matter, is can you construct any polygon? And the simple answer that I would offer my students is that you can't construct every polygon. You can construct infinitely many of them, since infinitely many polygons do exist under a certain theorem that we're about to talk about, but there are going to be polygons that aren't going to fit into the category of being constructible. So, this really gets at the heart of a theorem that is going to dictate whether a polygon is constructible or not, and that's the Gauss-Wanzel theorem. And the Gauss-Wanzel theorem says this: if you have a regular n-gon, so you have a polygon with n sides, regular meaning that all of the sides are going to be the same length, that n-gon can be constructed if and only if n, which is the number of sides, it can be written as the product of a power of 2 and any number of distinct Fermat primes, including no Fermat primes. So there's a lot going on in this theorem. Notice that it's an if and only if. We're going to go in both directions, okay? And this product of a power of 2, this last phrase is what's going to be most important. If and only if n is the product of a power of 2 and any number of distinct Fermat primes, including no Fermat primes. So we're going to talk in just a minute about what a Fermat prime is. That's obviously not a term that our students are going to be familiar with, and it was only one that I was kind of tangentially familiar with. But this is including no Fermat primes. So just to give you a little idea about how this could play, is I know that I can construct a regular quadrilateral, I can construct a square or a rhombus, and 4 can obviously be written as a product of a power of 2. And no Fermat primes. Okay? Same thing can happen if I can construct an octagon. 8 can be written as the product of a power of 2 and no Fermat primes. So when you're dealing with those shapes, you're not going to have any of these weird Fermat primes, whatever numbers those might be. But moving forward, those Fermat primes is what really makes it possible for us to create that 17-sided figure. So we've played with constructible figures, constructible n-gons, that are a product of a power of 2 and no Fermat primes. So if we're considering the ones that are a product of a power of 2 and no Fermat primes, obviously that's our rhombus, our square, and then we have another power of 2, we have an octagon, we have another power of 2, we have a 16-gon, we have another power of 2, we have a 32-sided figure, and so on and so forth. But we can make lots of other stuff too. And that's where we need to know what a Fermat prime is, so we can figure out what numbers are permissible under the Gauss-Wanzel theorem. So what you have here are the 5 known Fermat primes. A Fermat prime is a number that can be written in the form of 2 to the 2 to the n plus 1. So these are the Fermat primes we know, and then this should help us understand why we can construct some of the polygons that we already know pretty well. So our first Fermat prime is 2 to the 2 to the 0 plus 1. Well, right here, anything to the 0 power just becomes 1. So this is just 2 to the first power plus 1, which is 3. And so we can construct our equilateral triangle because of that. Next, we have 2 to the 2 to the 1 plus 1. Well, that's really 4 plus 1. So we can construct a regular pentagon, and that's a construction that many students do in a high school geometry class, that construction that Euclid did himself. Okay, next we got 2 to the 2 to the 2 plus 1, and hopefully you can see this pattern starting to emerge. Well, that's 16 plus 1. So there's our 17-sided figure, and that's the figure, remember, that Carl Gauss himself was able to construct that really led us down this thinking of, well, what can we do? Then we have 256 plus 1 and 65,536 plus 1. And so these Fermat primes open up new possibilities for what our constructible polygons can be. Remember that you need to be able to be written in a product of 2 to some power and a Fermat prime, or no Fermat primes at all, or multiple Fermat primes. So moving forward, we're going to be using that fact a little bit. So there are 31 combination of Fermat primes, so there are 31 odd constructible polygons that stem from this fact itself. Then what you can start doing is you can start doubling the number of sides, because remember the Gauss-Van Zyl theorem says that your polygon needs to be a product of a power of 2. So that's how we can arise with some of these other polygons as you see below. 3 is our Fermat prime. 3 is our Fermat prime, but then we can double the number of sides, and 6 can be written as 2 times 3. 12 can be written as 2 squared times 3. 24 can be written as 2 to the 3rd times 3. So you see that product of a power of 2 coming out really strongly here. Now we can think about what we can't do. So 7's a prime number. 7 can't be written as a product of a power of 2 and a Fermat prime. It's not constructible. There are a lot of other polygons that aren't constructible either. So 9 isn't prime. 9 can be written as 3 times 3. And 3 itself is a Fermat prime. But we can't write it as, oh dear. So for example, 9 is not prime. It's a product of 3 times 3, but it's not constructible because it's not written as the product of a power of 2 in any combination of Fermat primes. So here are some things we can go through what we can do. These are going to originate at some of the original constructions that Euclid himself was able to complete. So triangle is the product of a power of 2. Square is the product of a power of 2 and no Fermat primes. Pentagon is the product of a power of 2 and a Fermat prime. A hexagon is the product of a power of 2 and a Fermat prime. And so what we can start doing is start building up what we're able to do. And this next slide is going to show that really interestingly, all the things that we can construct. So this is a super interesting fact, or super interesting. Here you're going to be able to see it a little bit better. I'm trying to make sure that everything's going to fit into my screen. So what we have going on here is we've got a color-coded list of our constructible polygons and then where they arise from. So let's walk through, for example. We start with 3, which is a Fermat prime. From 3 we can get 6 because that's a product of a power of 2 in our Fermat prime, to 12, to 24, to 48, 96, 192, and 384. And all of those come from the original construction of 3, and then all we do is we continue to add powers of 2. If I want to give us another color to start color coding this, here's our infamous 7. Okay, I arrowed that because that's where we were living at with Gauss. And 17, remember, is our constructible number, and that comes from being a Fermat prime itself. 34 is 2 times 17, and then 68 is going to be 2 squared times 17. Drawing on this is really hard. And that gets us to 68, 136, and 272. And so what you can see in this table, and what I find really fascinating, and this is an article that I will link to at the end of my resources. This is really interesting to take a look at, is it kind of shows you where some of these families are coming from and why you can construct some of these. And so we see new families start to arise. For example, if we look at 15, 15 is a product of a power of 2, although that product of a power of 2 is 2 to the 0, times 2 Fermat primes, 3 times 5. And so that color shows that we're starting a new family here. Then we get our 15 to 30, to 60, to 120, to 240. And that comes from the fact that that's the product of our two Fermat primes that are coming together to give us that creation there. Moving on, there's just one more that I want to highlight here, and that one's 85. So 85 is 17 times 5. And once again, I apologize, writing on a screen is really difficult. So those are our 2 Fermat primes. Our product of a power of 2 is going to be 2 to the 0. But then from 85, okay, we can double ourselves and end up at 170. And then follow that orange family tree down. And obviously this could keep going and going and going. There are infinitely many numbers that we can start thinking of if we just continue to add on powers of 2. So I think this slide is a really interesting way to start figuring out where those families are coming from. Our yellow numbers are coming from our products of power of 2 and no Fermat primes. So those are just our powers of 2 right there. Okay, let me erase this stuff so we can continue on. I thought this is probably the most interesting thing that I was able to come across in my research. It really visually shows us what's going on. So if we want to start our follow-up with one of our students, this is a question that I would ask them. I might not necessarily have given them that table, but I would want them to be able to understand how you know a 40-sided figure is constructible. And I worded it in that way specifically, explain how you know. I don't want students to answer the yes or no question and then try to follow up with and explain. This does give them the scaffold of knowing that they're working towards something versus trying to figure out if something's true or not. So this is a question I could ask, or I could come up with any number of numbers from this screen and explain to me why that number is constructible. 40 seemed to be a little bit easier for my students to handle. Most of my students, I teach at the 10th grade level at Penta. Many of my students are currently doing math below grade level and feel really, really a lack of confidence with math. So I wouldn't throw something like 320 at them right away, or 384 or something like that. I could, but this is going to help me understand that they can apply the Gauss-Wanzel theorem. So what I would expect from them is that they know that 40 must be written as a power of 2 and some number of Fermat primes or no Fermat primes at all. In this case, 40 can be written as our 2 to the 4th times 5. And so therefore we know that 40 is a constructible number and therefore a constructible polygon under the Gauss-Wanzel theorem. Something else that they could also say is they could say, for instance, that they know that, if we work backwards that table again, it's really just a great table, okay? If we were able to work backwards, 40 comes originally from being able to create a pentagon. So if they knew that in class they were able to create a pentagon and then explain that they know that they could continue to double the number of sides by bisecting an angle again and again, and that would arrive at a 40-sided figure, that's a really interesting alternate explanation. It might be something that would be a really great explanation if I didn't go into depth on the Gauss-Wanzel theorem. So that concludes my presentation. What you have on the screen are the resources that I used for this presentation. Going through the first resource is just talking about how to do some basic constructions. That was from the mathematics teacher. It's definitely an older article. Obviously, I referenced the Common Core state standards that were relevant to our question. The next one is probably the most pivotal article that was helping to guide my research. The Jones article, Regular Polygons in the Place of Geometry in Mathematics. That comes from, or that's where I got this chart from that was really important to helping us understand what was going on. It also does a really good job of trying to tie in the algebra. The algebra is a little bit more difficult. The solving of the polynomials that help you understand what a constructible number is really cool, but wouldn't necessarily be relevant to students. Most of my students are taking geometry after just an Algebra 1 course, so it really wouldn't have helped their understanding. And then the Slavic article is talking about specifically similarity and congruence, and that's going to be helpful. And then finally, the textbook, at the end of the textbook, talks about kind of the construction problems of antiquity, and that was some really interesting background reading to think about the questions that any mathematician would be asking, and understanding that our students, despite maybe not being as knowledgeable in mathematics or having the experience, they might be asking those exact same questions. So thank you for your time listening to this presentation. I hope it was helpful for you. Please feel free to reach out to me if you've got any further questions or want to talk about it more. Thank you.